Will the blight and the chestnut? The farmers rather guess not. It keeps smoldering at the roots and sending up new shoots till another parasite shall come to end the blight. At the beginning of the 20th century, the Eastern American chestnut population, counting nearly 4 billion trees, was completely decimated by a fungal infection. Fungi are the most destructive pathogen of plants, including crop of major economic importance. Can you imagine that today crop losses associated to fungal infection are estimated to billions of dollars per year worldwide? That represents enough food calories to feed 500 million people. And this leads to severe repercussions, including episodes of famine in developing countries, large reduction of income for farmers and distributors, high prices for consumers, and risk of exposure to mycotoxin, poison produced by fungi. The problem that we face is that the current method used to prevent and treat those dreadful diseases, such as genetic control exploiting natural sources of resistance, crop rotation, or seed treatment, among others, are still limited or ephemeral. They have to be constantly renewed. Therefore, we urgently need to develop more efficient strategies, and for this, research is required to identify biological mechanisms that can be targeted by novel antifungal treatments. One feature of fungi is that they cannot move and only grow by extension to form a sophisticated network, the mycelium. In 1884, Anton de Barry, the father of plant pathology, was the first to presume that fungi are guided by signals sent out from the host plant, meaning a plant upon which it can lodge and subsist. Those signals act as a lighthouse for fungi to locate, grow toward, reach, and finally invade and colonize the plant. He knew that the identification of such signals would unlock a great knowledge that then served to elaborate strategy to block the interaction between the fungus and the plant. However, the lack of appropriate method at that moment prevented him from identifying this mechanism at a molecular level. Using purification and mutational genomic approaches, as well as a technique allowing the measurement of directed hyphal growth, today, I'm glad to tell you that after 130 years, my former team and I could finally identify such plant signals by studying the interaction between a pathogenic fungus called Fusarium oxysporum and one of its host plant, the tomato plant. As well, we could characterize the fungal receptor receiving those signals and part of the underlying reaction occurring within the fungus and leading to its direct growth toward the plant. Thank you. Thank you. The understanding of such molecular process offers a panel of potential molecules that can be used to create novel antifungal treatments. And those treatments would disrupt the interaction between the fungus and the plant, either by blocking the plant signal or the fungal reception system which receives those signals. Fungal infections have devastated agriculture crop. Moreover, we are now in an era where the demand of crop production is increasing significantly. And this is due to population growth, economic development, climate change, and demand for biofuels. Our understanding of the molecular mechanism of interaction between a fungus and its host plant, such as the tomato plant, potentially represent a major step toward developing more efficient strategy to combat plant fungal diseases and therefore solving a problem that affects people's life, food security, and economic growth. Thank you.